Hi, welcome back to KIG1015 Dynamics. To recap back what we have discussed in our last lectures, the difference between statics and dynamics. In statics, we analyze the conditions of bodies at rest. We utilizing equations of equilibriums. Whereas in dynamics, we are analyzing the conditions of bodies in motions. So dynamics includes kinematics and kinetics. Kinematics is the studies of the geometry of motions, where we relate displacement, velocity, accelerations, and times, without the reference to the cause of motions. In other words, without considering how the force acting on the bodies. Whereas in kinetics, it's the studies of the relation between the forces acting on the bodies, the mass of the bodies, and the motions of the bodies. Here, we include the effects of the force on the bodies. So we can predict the motion caused by the given forces, or we determine the forces required to produce the given motions. In dynamics, we apply equation of motions. So in this course, we are looking into two types of bodies. First, the dynamics of particles, followed by the dynamics of rigid bodies. The particles are not limited to the size. By saying so, when the bodies are analyzed as particles, it means that their motions as an entire unit will be considered. Any rotation about their own mass center will be neglected. However, in the cases where the rotation is not negligible, the bodies cannot be considered as particles. So the motions of this body have to be dealt with dynamics of rigid bodies. So for the start, we will be looking into the dynamics of particles. We first start with the kinematics of particles, followed by the kinetics of particles. Once we have completed the dynamics of particles, then we can move to a more advanced topics on dynamics of rigid bodies. Again, the same, we will start with the kinematics of rigid bodies, then finally we will touch on the kinetics of rigid bodies. So today, we'll be looking into the kinematics of particles, particularly on rectilinear motions. This is the outline of today's lectures. We'll start with the introductions of kinematics of particles, particularly on rectilinear motions in terms of positions, velocity, and accelerations. We also look into the determination of motions of the particles. Here, the rectilinear motions of particle will be analyzed in terms of the positions, velocities, and accelerations of the particles will be determined at every instant as it moves along a straight line. So the keywords here is rectilinear motions, straight lines. Some general methods of analysis will be used to study the motions of the particles. The two important particular cases will be considered here. First, the uniform rectilinear motions, then the uniformly accelerated rectilinear motions. The simultaneous motion of several particles will be considered. The concept of the relative motions of one particle with respect to another will be introduced. Here is called relative motions, followed by dependent motions. And finally, the graphical methods of analysis and their applications to the solutions of various problems involving rectilinear motions of particles will also be discussed at the end of these lectures. Let us have a look on why we are studying kinematics of the bodies. here is referred to particles. Kinematics relationships are used to help us to determine, for example, the trajectory of a golf ball, the positions of the golf ball over time, how it moves, the orbital speed of a satellite over times, probably, and the accelerations during the acrobatics flyings. We can say that kinematic studies help us to relate the parameters such as the positions, the velocities, the accelerations of bodies. Here is referring to particles at the time instance. Okay, at a certain times, we want to determine where is the positions of the particles, the velocity of the particles, or the acceleration of the particles. So this is about kinematic studies. As I mentioned earlier, dynamics includes kinematics and kinetics. So kinematics is the study of geometry of motions. We relate displacement, velocity, accelerations, and times. Here, without reference to the cause of motion, meaning without the reference of the force. No information of the force. We are particularly interested on the displacement, velocity, and accelerations over times. Whereas kinetics is a study of the relationships existing between the forces acting on the bodies, the mass of the body, and the motion of the body. So here we include how the force acting on the bodies or the particles, then how the force causes the motions of the particles. Kinetics is used to predict the motions caused by given forces or to determine the forces required to produce a given motions. When we say dynamics of particles, so it includes two types of motions. The first one is the rectilinear motions. So here we are saying that the positions, the velocities, and accelerations of particles as it move along a straight line. So rectilinear motion is referring to straight lines motions. Whereas another types of motions under these particles dynamics is curvilinear motions. In curvilinear motions, positions, velocities, and accelerations of particles, it will move along a curved line in 2 or 3 dimensions. So here, in the kinematics of particles, we have two types of motions. First is a rectilinear motions, moving along straight lines. Next is a curvilinear motions, moving along the curved line. A particle moving along a straight line is said to be in rectilinear motion, as mentioned just now. At any given time instant t, the particle will occupy a certain position on the straight line. To define the position p of the particle, we choose a fixed origin O on the straight line and a positive directions along the line. Here, we measure the distance x from O to P and record it with a plus or minus sign, according to whether P is reached from O by moving along the line in the positive or negative directions. The distance x with the appropriate sign, basically it completely defines the position of the particles. It's called the position coordinates. So position coordinates is defined by positive or negative distance from a fixed origin on the line. So for examples, the position coordinates corresponding to P is x equals to plus 5 meters, whereas the position coordinates of P primes is equals to negative 2 meters. The motions of a particle is known if the position coordinates for particle is known for every value of time t. This motion can be given in the form of equations in x and t, as you can see here, or in the form of graph x versus t. The units most often used to measure the position coordinates x are the meters in the SI system of units, or the foot in the US customary system of units. Time t is usually measured in seconds s. Consider the position p occupied by the particles at time t and the corresponding coordinate x. Consider also the position p primes here occupied by the particles at a later time t plus delta t. The position coordinate of p prime can be obtained by adding to the coordinates x of p the small displacement delta x, which will be positive or negative according to whether p prime is to the right or to the left of the p. The average velocity of the particles over the time interval delta t is defined as delta x over delta t. If SI units are used, delta x is expressed in meters and delta t in seconds. The average velocity will thus be expressed in meter per second, MOS, whereas when US customary units are used, delta x is expressed in feet and delta t in seconds, and now the average velocity will be expressed in feet per second. The instantaneous velocity v of the particle at the instant t is obtained from the average velocity by choosing shorter and shorter time intervals delta t and displacement delta x. So here, instantaneous velocity is expressed as v equals to, when the limit of delta t is approaching 0, delta x over delta t. It is also can be defined as the derivative of x with respect to t. Or here we say it is v equals to dx dt. A positive value of v or instantaneous velocity indicates that the x increase. The particles move in the positive directions. Whereas a negative value of v indicates that x decrease. The particle move in the negative directions. The magnitude of v is known as the speed of the particles. So the instantaneous velocities v is defined as the derivative of x positions with respect to t, or dx dt. So it can be expressed in the form of the equations of v over t, or in the form of graph of v versus t, as you can see here. So what it means here, if we have functions of position over times, finding the derivative of these position functions, we will get the velocity functions over times, v equals to dx dt. So now, if we consider the velocity v of the particle at time t, also its velocity v plus delta v at a later time t plus delta t, the average accelerations of the particle over the time interval delta t is defined as delta v over delta t. So here, if you want to determine average accelerations, so it is defined as delta v over delta t. If SI units are used, delta v is expressed in meter per second and delta t in seconds. The average accelerations will thus be expressed in meter per second square. If you are using US customary units, delta v is expressed in feet per seconds and delta t in seconds, and then the average accelerations will then be expressed in feet per second square. Next, the instantaneous accelerations A of the particles at the time instant t is obtained from the average accelerations by choosing smaller and smaller value of delta t and delta v. So here instantaneous accelerations equals to A equals to when the limits of delta t is approaching 0, delta v over delta t. So it can be rewritten as A instantaneous accelerations equals to dv dt. So A equals to dv dt, or is defined as the derivative of the velocity of the particle v with respect to time. The instantaneous acceleration may be positive when we have an increasing positive velocity as shown here, or decreasing negative velocities. Both will give positive instantaneous accelerations. The instantaneous acceleration could be negative when we have a decreasing positive velocities or increasing negative velocities. The term decelerations is sometimes used to refer to A, the instantaneous accelerations when the speed of the particles, the magnitude of the v, decrease. The particles is then moving more slowly. From the definitions of the derivative, the instantaneous accelerations A is defined as dv dt, or if the position function is given over times, then it will be d2x dt squared. So the instantaneous accelerations A can be given in the form of the functions A over t, or in the form of graph A versus t. When the position coordinates, the velocity and the accelerations are plotted against t, as we have shown just now, these curves obtained are known as motion curve. Please keep in mind that the particles does not move along any of these curves. The particles are in rectilinear motions, moving in a straight line. In practice, however, a motion is seldom defined by a relation between the position and time x and t, velocity and time v over t, or acceleration and time a over t. In general, a particle can be expressed as a function of one or more of the variables. We often determine accelerations from the forces applied. This is related to kinetics of particles, where the force is included, which will be covered in the later topics. Generally, there are three classes of motions, besides what we have learned just now, whereby the accelerations is given as a function of time, a equals to ft. The accelerations of the motions of the particles can be also given as a function of positions, a equals to fx. Or the accelerations can be given as a function of velocity, a equals to fv. Can you think of a physical example of when force is a function of positions? The springs. So when we compress or expand the springs, then we have the positions. So it's a function of accelerations of force with positions. Then how about when the force is a function of velocities? The drags from the jets. Right? So you have the drag force proportionals or the functions as a functions of the velocity of the jets. So acceleration as a function of time, position, or velocity. So if your accelerations given is a function of times, then the kinematics relationship that we have learned just now is at equals to dv dt. Integrate it, you have the velocities from the acceleration function. And if our acceleration functions is given as a functions of position, ax, the kinematics relationship that we can build is a equals to dv dt that we have learned just now, or the dx dt equals to v, or here is dt equals to dx over v. So building from here, we can have our v dv equals to ax dx. Integrate this, we have our velocity functions v, okay, from our ax, or the acceleration functions in terms of positions. Next, if our acceleration function is given in terms of velocities, av, we can build from a equals to dv dt. So from here, we can find the time informations, okay, from this acceleration function in terms of velocities. Besides this, we can build another kinematic relationships, av equals to v dv dx. So from here, we do the integrations, we will have the position informations, all right, from these acceleration functions in terms of velocities, av. So by now, we should be able to make use of these kinematics relationships that we have discussed so far to relate the positions, the velocities, the accelerations, and the time of a particles. From there, we can find its trajectories, its velocities, its accelerations at particular instant of time. When we want to study the motions of our particles, there are two important particular cases that need to be considered. One is called uniform rectilinear motions. Another one is called uniformly accelerated rectilinear motions. So what is uniform rectilinear motions? So during a free fall, a parachutist reaches a terminal velocities when her weight equals to the drag force. So in this case, if motion is in a straight line, this is a uniform rectilinear motions when the velocities in this case is constant. So what it means here, for particles in uniform rectilinear motions, the acceleration is zero and the velocity is constant. Recap back what we have learned just now, v equals to dx dt. So here the v, or the velocity, is constant. When it is constant, it is called uniform rectilinear motions. So deriving from these equations, we will have our x minus x naught equals to vt, and our x, or the positions, equals to our initial position plus vt. So remember, this only applicable to the uniform rectilinear motions when your particles or the bodies is in constant velocities or zero accelerations. Another types of motions is called uniformly accelerated rectilinear motions. So these are the examples. So if forces applied to a body are constants and in a constant directions, meaning you have a constant accelerations, then Here we are saying that we are having a uniformly accelerated rectilinear motions. Another example is the free fall objects. When the drag is negligible, you have a constant gravitational accelerations, then that is also under uniformly accelerated rectilinear motions. For a particles in uniformly accelerated rectilinear motions, the accelerations of the particles is constant. Remember, the acceleration is constant. So you may recognize this constant acceleration equation from your physics courses. We have done this before in our physics course. Another three equations can be derived from here based on the dv dt equals to accelerations, and when this acceleration is constant, we can find or derive an equations v equals to v naught initial velocity plus a t. We can also use this dx dt, which is our v, right, equals to v naught plus at from here to derive our accelerations and velocities and also position relationships. So in this case, the positions of the particles x equals to x naught, the initial position, plus v naught t plus 1 over 2 at squared. This is the second equations that we can derive from these uniformly accelerated rectilinear motions. And finally, we can use v dv dx equals to a and is equals to constants. So from here, we can build the relationship between the positions, the velocity, and the accelerations. Here, the velocities square equals to the initial velocity square plus 2 accelerations multiplied with the x minus x naught, your position difference. Remember, this only applies to uniformly accelerated rectilinear motions. Those particles in constant accelerations, we can apply these three so-called equations. Next, motions of several particles. We may be also interested in the motions of several different particles, whose motions may be independent or linked together. When several particles move independently along the same lines, independent equations of motion can be written for each particle. Whenever it's possible, time should be recorded from the same initial instance for all particles, and the displacement should be measured from the same origin and in the same directions. In other words, a single clock and a single measuring tape should be used. For a particle moving along the same lines, the time should be recorded from the same starting instance, and the displacements, as I mentioned just now, should be measured from the same origin in the same directions. Taking the two particles A and B moving along the same straight line as you see here, if the position coordinates XA and XB are measured from the same origins, the difference between the two particles, XB minus XA, define the relative position coordinates of B with respect to A. So here, the XB over A is the relative positions of particles B with respect to particle A. So it's equals to XB minus XA, or we can rearrange it equals to XB equals to XA plus XB over A. So this applies to the velocities. So the rates of change of XB over A is also known as the relative velocity of particle B with respect to particle A. So it's denoted by VB over A. So VB over A is equals to VB minus VA equals to relative velocity of B with respect to A. Or we rearrange it, VB equals to VA plus VB over A. So a positive sign of VBOA means B is observed from A to move in positive directions. A negative sign means that it is observed to move in negative directions. Finally, the rate of change of VBOA is known as the relative accelerations of particle B with respect to particle A and is denoted by ABOA. So as you can see here, ABOA equals to AB minus AA is a relative accelerations of B with respect to A. If we rearrange it, AB equals to AA plus ABOA. Sometimes the position of a particles will depend upon the position of another particles or several other particles. These motions are said to be dependence. So under dependent motion, the position of a particle may depend on position of one or more other particles. It can be commonly seen in the pulley system as shown here. So basically we can make use of the constant length of the ropes to build a relationships. So for example, positions of block B here depends on the position of block A. So since the rope is a constant length, so it must follow the sum of the length of the segments must be constant. The rules is there. So the rope's length is constant and give us a relationship of XA, the length here, plus 2XB, 1 and 2 is the constant length of the ropes. Since only one of two coordinates XA and XB can be chosen, we can say that this system has only one degree of freedoms. From the relationship between the positions coordinates XA and XB, it follows that if XA is given an increments delta XA, that is, if block A is lower by an amount delta XA, going down delta XA, the coordinates XB will receive an increment delta XB equals to negative 1 over 2 delta XA. In other words, block B will rise by half the same amounts. This can be easily be checked directly from the figures. In the case of 3 blocks systems, we can again observe that the length of the rope which passes over the pulleys is constant. So we can build the relationships and equations consists of 2XA, 1XA, 2XA, plus 2XB, 1XB, 2XB, plus XC, right, is equal to a constant. So here we are saying that it's a 2 degree of freedoms because 2 of the coordinate can be chosen. For linearly related positions, similar relations hold between velocities and accelerations. So from the position equations that we have built just now, if we differentiate once, we will have the velocity relationships. So it will give us 2VA plus 2VB plus VC equal to 0. If it differentiates again another times from the velocity equations, then we will have the acceleration equations equals to 2AA plus 2AB plus AC equal to 0. So from these relationships or equation builds, then we can determine the dependent motions of the particles, particularly on a pulley system as shown in the figures here. Finally, we look into graphical solutions of rectilinear motion problems. A lot of time, engineers often collect position, velocity, and accelerations data. These graphical solutions are often useful in analyzing this data. For examples, the acceleration data from a head impact during a round of boxings, it will create an accelerations, very short impulse accelerations over a very short period of times, right? So if you plot the accelerations over times, that give us the impact profiles as you've seen in terms of accelerations over times. And this is a very common engineering data in terms of accelerations over times that we may collect practically using sensors. So what we can derive from the motion curve as you've seen here. Given the xt curve, the position over time curve, the vt curve is equals to the xt curve slopes. The slope of the xt curve gives us the vt curve. Whereas given the vt curve, the at curve is equals to the vt curve slopes. What it means here, if you can get or determine the slope of the vt graph, the velocity over time graph, then we will be able to plot the accelerations over time graph or at curve. In the reverse way, given the accelerations curve, accelerations over time curve, the change in velocity between the time 1 and time 2, t1 and t2, is equals to the area under the at curve between t1 and t2. So if you are given a at curve, the acceleration curve, the area under this curve itself over the time 1 and time 2, it basically gives us the change in velocities. And finally, given the vt curve, the change in position between t1 and t2, we can determine the positions basically from the area under the vt curve between t1 and t2. So this area under the vt curve between t1 and t2 basically gives us the positions or the change in position between t1 and t2. So to summarize these topics, kinematics, rectilinear motion of particles, we have learned how to determine the positions, the velocity, or the accelerations of a particle in rectilinear motions. It's also important that we identify both the independent variables, typically t, time, or x, the position coordinates, and what is required. For example, we need to express the v, the velocity, as a function of x, the positions. So it may be helpful to start each problems later on by writing down both the given informations and a simple statement of what is to be determined. In these topics, we also derive the equations that describe the uniform rectilinear motions, those in constant velocities, and uniformly accelerated rectilinear motions, those in constant accelerations. We also introduce the concept of relative motions. So you can apply the equation for the relative motions to the independence or dependent motions of any two particles moving along the same straight lines. And finally, we learn several graphical techniques for the solutions of problems involving rectilinear motions. This technique can be used to solve problems directly or to complement the analytical methods that we have learned. It will provide a visual descriptions and thus a better understanding on the motions of a given body, here particularly is the particles. That's all for the topics of kinematics of particles, rectilinear motions. In our next lectures, we will be covering again the kinematics of particles, but on curvilinear motions of the particles. Thank you.